Hello everyone, welcome back to the world of STEM. Today we will be discussing 1D kinematics, which is a fundamental unit in the AP Physics 1 and the Physics Honors curriculum, and it's usually one of the first units that is discussed in physics. Alright, so to begin, let's talk about position. So position is a vector with both distance and direction. Vectors are usually defined with both a distance and a direction. So when you say position, an example position would be 2 meters I hat, which is usually a direction to represent the orientation on the x-axis, or 6 meters north. So there's a distance given and a direction given. Delta x, so the triangle represents delta. Delta x is usually defined for horizontal position, and delta y is usually defined for vertical position. And also, when problems mention objects in rest, which is commonly discussed in physics, you can define object in rest based on its position over time. So when an object is in rest, that basically means there is no change in position over time. Alright, so here's a graph that's depicting position versus time. And on the graph, at a certain time, if you want to find the position, just draw it up to the graph. So at time t equals 3 seconds, the position is 9 meters, and let's call the units over here north. So it's 9 meters north at time t equals 3 seconds. Cool. So now let's talk about displacement and distance. And understanding the difference between these two quantities is actually fundamental in several problems where they ask you to calculate the displacement and distance individually. And many students usually get confused with understanding the difference or what exactly each one of them represents. But hopefully I can explain this clearly over here. So displacement is what's called the object's change in position. When talking about displacement, you're only talking about the object's starting point and the ending point, and the change between the start and the end. What the path that the object takes between the starting point and the ending point does not matter in this context for displacement. Displacement is also what's called a vector quantity. So in a vector quantity, there is both a magnitude and a direction. And distance, on the other hand, is how much ground an object covers. So that's usually basically there is a starting point, there's an ending point in distance also, but then the path that it takes matters. Path matters under distance. And distance is a scalar quantity, which means it only has a magnitude, which means also distance always has to be positive because there's no sign convention to define a negative from. So it's a scalar quantity. Let me write that out. Which means it only has magnitude. And yes, it is very important to understand the difference between these two quantities, as I mentioned earlier. So let's look at a graph here to help us understand this concept. So let's say there's an object, let's call this north again. It means the object is moving up, but the graph is position versus time. And let's have both the displacement and the distance. Alright, so in displacement, it's at 6 meters at time t equals 0. And okay, let's all calculate both displacement and distance from time t equals 0 to 24 seconds. And this is at 24. So the displacement in this case is the change in position. And the change in position, it started at 6 and went to 0. So the change is final minus initial, which is actually negative 6 meters north. That's a displacement. However, the distance over here is the total ground covered. So you have to calculate every meter that this object traveled, not just from the start to the end point. So until 8 seconds, the position stays at 6, which means the distance traveled there is 0. It's at rest until 8 seconds. And then from 8 to 16 seconds, it goes from 6 to 15. So that's 9 meters that it traveled, 15 minus 6. And then from 16 seconds to 24 seconds, it goes all the way from 15 to 0. So during that point, it went 15 meters. There's no direction again, so it doesn't matter if it's going up or down. In reality, it went 15 meters south from 16 to 24, but because we're talking about distance and it doesn't have a direction, we always use the magnitude. So even if that was negative 15, we use the magnitude of that, which is still 15. So the total distance here is actually 9 plus 15, which is 24 meters. Sorry, pardon my handwriting. All right, so 24 meters is the distance in that example. Cool. Okay, so now let's talk about velocity versus speed and try to understand the difference here again. Velocity is the rate of change of position with respect to time. So what this means is if you have an object at a position of 2 meters and an object at and then it goes to 5 meters in 1 second, your velocity is the rate of the change of this position. So the change of the position was 3 meters, and the rate of change happens with respect to time, so in 1 second. So your velocity in that case would have been 3 meters per second, and let's call this to the right, because we went to the right. Like I said, there's a magnitude and a direction because velocity is a vector quantity, which means you have both. Speed is the magnitude of velocity. So speed is actually what we call a scalar quantity, which means only the magnitude, no direction. So speed is similar to distance, and velocity is similar to displacement, like we showed from the previous slide. And there's also a way to calculate average velocity and average speed. Average velocity is displacement over time. Average speed is distance over time. We'll cover this in the next slide where there's an example problem. All right, so we have that a person walks 5 meters north and 3 meters south in 4 seconds. And we're asked to find the average velocity and the average speed. So we're starting at x equals 0. Person goes 5 meters north, and then they go another 3 meters south. And let's draw the 5 better. Okay, so, and this happens in 4 seconds. So first of all, we need to calculate the displacement, then we need to calculate the distance. So the displacement in this case, it only compares the starting and the ending points. So you went 5 minus 3, so you end up at 2 meters north, and you start at 0 meters north, and you end up at 2 meters north. So the displacement is just 2 minus 0, which is 2 meters to the north. And the distance in this case, however, is you went 5 meters initially, and then you went another 3 meters. This all happened in the north direction, so 8 meters north is the distance. So average velocity is displacement over time, which should equal 2 meters north over 4.00 seconds, 0.50 meters per second north. That's the average velocity. And the average speed is distance over time, which I'll get it all the way over here. It should be 8 meters second north over 4.00 seconds, which is equal to 2 meters per second. And like I said, the average velocity is a vector, so it has a direction also, but average speed has no direction, only magnitude. Cool. Now let's talk about acceleration. Acceleration, like velocity, is the rate of change of position with respect to time. Acceleration is the rate of change of velocity with respect to time. And usually when kinematics, you only deal with constant acceleration, but there are also situations in physics where your acceleration is variable. So sometimes it accelerates at a faster rate, sometimes it accelerates at a slower rate. And also there's a formula for average acceleration, which is actually quite intuitive when you think about it, but it's just the change in velocity over the change in time. Average velocity was the change in position over change in time. Yeah, so to review average acceleration, let's look at this example problem that I have here. So we have that a car accelerates to 40 meters per second from 50 meters per second in 6 seconds. They're asking for the average acceleration. So first we have to find the change in velocity. which in this case, let's say it's going to the right. So you can say to the right, TTR to the right. So change in velocity is actually 40 meters per second minus 15 meters per second. This is all to the right. And sorry, don't need to divide quite yet. So that would be 25 meters per second to the right. And then because we know the formula for average velocity, average acceleration, average equals, change in velocity over change in time. So that would mean the change in velocity is 25 meters per second. And then time is 6 seconds. And we're going to the right, which means our average acceleration is 25 over 6 meters per second squared to the right. That's an example where we calculate our average acceleration. And now let's talk about analyzing graphs in physics. So there are basically 3 major graphs that we look at, which is the position, velocity, and the acceleration graphs. And there's key features like the slope or the area under certain graphs that represent certain variables. So in a position versus time, the slope is average velocity. And this is logical when you think about it. If you have 2 points with positions, and the slope is basically the average rate of change between the 2 points, the average rate of change of position with respect to time is velocity. Velocity is the rate of change of position with respect to time. So average rate of change would be average velocity. And average rate of change is basically what a slope is. By the same logic, in a velocity versus time, the slope would have to be average acceleration. There's also this key thing where the area under the velocity versus time graph is displacement, because that represents change in position. And then the area under acceleration versus time is change in velocity. There's a slope for acceleration versus time, which is the rate of change of acceleration, which is jerk, but that is almost never asked of. So that's just trivia knowledge, if anybody was interested. Yeah, so the rate of change of acceleration with respect to time is called jerk. And then if any peeps are in calculus, there are some applications of calculus to find instantaneous quantities. So there's instantaneous velocity, instantaneous acceleration. And you can find that by using the slope of tangent line at a specific point. So if you have this 2 to 4 at 3, actually this is not, let me draw a better graph. So if you have something like that, which is 2 and 4, and let's say 3 happens there, the slope of a tangent line at x equals 3 would be, when you draw a tangent line, it would be the slope of that line, m of line 1. Let's call this line 1. But yeah, that's just an interesting calculus application. So I've set some graphs here for us to find certain things to kind of hopefully nail this concept in. So here we have average velocity from different times that we're asked of. So from the average velocity on a position versus time graph is the slope. So from 1 to 3 seconds, 3 to 6, and then the slope of this would be 6 minus 3 over 3 minus 1, which equals 3 over 2 meters per second. And let's just call this I hat as our sign convention. All right, 2 to 4 seconds. So we start off at 6, we go to 9, and that should again just be 3 over 2 meters per second I hat. And then finally from 1 to 5, which we're at 3, and then we end up at 3. So if you see, the displacement here is basically 0. So you know our average velocity is 0. But even using the slope formula, 3 minus 3 over 5 minus 1, top is 0, so bottom, the entire equation is 0. So that's the average velocity from 1 to 5. We have velocity versus time graph over here. So here the average acceleration is the slope. So from 1 to 4 seconds, you can see at 4 seconds, it's actually at 3 meters per second is the velocity at 4 seconds. So the average acceleration from 1 to 4 is 3 minus 2 or 4 minus 1. And let's all use the same sign convention, which is 1 over 3 meters per second squared I hat, or approximately 0.33 meters per second squared I hat. All right. And then part B is displacement from t equals 1 to 4. And the displacement of the graphs are actually found by calculating the area under a graph. So here I've divided it into some figures here to geometrically assist you. But usually when you find this area under the graph, which you're sometimes asked to do, and sometimes it's easy shapes, sometimes it's harder shapes. You could do this in multiple ways. I'm just trying to make it obvious with what I'm trying to do here by breaking it up into rectangles or triangles, but you can also break it up into trapezoids to use lesser figures. And when you find whatever, and so the displacement will be all these individual areas added together, but displacement from a certain time to a certain time is basically the area under the curve. So again, acceleration, average acceleration from t equals 1 to 3. This actually does not even need to be a slope. When you just think about it, at t equals 1, it was 4. At t equals 2, it was 14. The average acceleration is just 4 plus 14 over 2. It's actually just 10 meters per second squared I hat. And then for 2, you can total change in velocity is the area under an acceleration versus time graph. And here you could solve this by using trapezoids actually. It's terrible drawing, but hopefully you get the idea here. By using 2 trapezoids, T1, T2, and finding the area, you're basically finding the area under this curve, which should give you the total change in velocity. And finally, we'll talk about the principal kinematic equations, which are essential to solve one-dimensional motion problems, and they relate basically velocity, acceleration, time, and displacement together. So there are 4 fundamental equations, and I'll just read each one of them out so you understand the sign convention. The first one is final velocity is the initial velocity plus acceleration times time. The second one is displacement or change in position is the initial velocity times time plus 1/2 times the acceleration times time squared. The third one is final velocity squared is the initial velocity squared plus 2 acceleration times displacement. And the fourth one is displacement or change in position is final velocity minus initial velocity over 2 times time. But this, when you think about it, is just average velocity. So the displacement is actually just average velocity times time. And you use each equation in a different case based on what variables you're given. So if you're not given time at all, not given t, no t, then you should notice that this third equation is the only one that doesn't have t, so you'd have to solve using this one. So basically use different equations in different scenarios, but this will be better explained with the 2 practice problems that I have set up. So let's firstly quickly work on this first one. So rock is thrown upward, they give you a speed, and they give you acceleration, they ask for the maximum height. So they're asking for displacement. You're given the initial speed, and you're given the acceleration. And at the maximum height, when you think about how a throw works, at this maximum height, for that specific instance, the object is not moving at all. So the velocity actually, final velocity at a maximum height is actually always 0. So you're also given final velocity. So going back here, no time, as we said, this is the equation that we should use. So using that equation, we have VF squared equals VI squared plus 2A times change in X. So we have VF squared minus VI squared equals 2A change in X. So we have change in X equals VF squared minus VI squared over 2A. So we might actually have to erase some things to give myself a little bit of space here. Alright, so me just do that real quick. Okay. That's, whoops. Alright, so coming back here. Our change in position or displacement would be velocity final is 0 meters per second. It's all defined in terms of j hat, which is actually the vertical direction in physics. Minus 12 meters per second squared j hat over negative 1.5 meters per second j hat. And when you solve that, you should actually get 48 meters j hat is the maximum height of the object. All right, cool. And then another problem here. In this problem, we're given the speed is 14 meters per second, the free fall acceleration is 3.5, and the speed of the hammer after 8 seconds. So at given time, you're given your initial velocity, given your acceleration, and you're trying to solve for final velocity. Not final velocity, but velocity at t equals 8. So given these variables, we can see that this equation is the one that contains all of them, so that's what we'll be using. So we have Vf equals Vi plus A times change in t, which means that the final velocity at 8 seconds would be the initial velocity, which is 14. They give you initial speed, but we can just assume it's moving to the right and use I hat as a sign convention. So 40 meters per second I hat plus your acceleration, be careful here, downward. Oh, actually it gave upward and downward, so we have to use J hat because that's the vertical direction. So that's a J hat plus negative 3.5 meters per second squared J hat. And then times our change in time, which is our 8 seconds. When you solve for this, you should get velocity final is 14 meters per negative 14 meters per second J hat, or 14 meters per second. You could say that is downward. But yeah, that's how you solve this problem. So basically, when you notice there, we use 2 different equations on 2 different problems based on the variables that were given to us. So it's important to recognize the variables you're given and use the appropriate equations that you can efficiently solve without having to use too many tedious steps. But with more practice, people usually get the hang of that. Anyway, this actually wraps up our video on 1D kinematics for today. So thank you so much for watching with the world of STEM. As always, please feel free to comment down if you caught any errors or any suggestions you have for future videos. And we'll always respond promptly to comments, and we appreciate the suggestions. And if you really enjoyed the video, please consider subscribing, liking, and sharing the video to other people so that we can benefit as many people as possible. Anyway, this is Pranav with the World of STEM signing off.